Die casting, a precision-driven and efficient metal manufacturing process, is a cornerstone in producing goods across industrial, commercial, and consumer sectors. Die-cast parts are renowned for their accuracy, making die casting a go-to process for creating complex metal components, especially in high-volume production scenarios. The die caster often works with primary materials such as aluminum, magnesium, copper, and zinc alloys, each offering unique benefits and being suitable for specific applications. How die casting works? Regardless of the die casting type, the process follows a routine. Here are the steps involved. Clamping. The initial stage involves readying the dies for casting. The two halves of the die, the cover die half and the ejector die half, are secured together. The gap between these two halves functions as the mold cavity. Injection. In the subsequent stage, molten metal is injected into the mold cavity under high pressure. The pressure degree depends on the material type and whether it is a hot chamber or cold chamber die casting machine. The pressure ensures that the material is forced into even the tiniest crevices of the mold. Cooling. Post-injection, the molten metal begins to cool and solidify within the mold cavity. The pressure is maintained during this stage to mitigate shrinkage and ensure the metal fills the cavity. Ejection. Once the metal has cooled and solidified, the casting is ejected. The dies are opened, and the castings are gently pushed out of the dies with ejector pins. Another shot can be prepared immediately after the ejection, enabling rapid mass manufacture of identical parts. Trimming. The final stage of the die casting process is the shakeout stage. It involves cutting the excess bits of metal attached to the casting, including flash from the parting line and any gates, runners, and sprues. Material considerations in die casting. Die casting employs a variety of metals, predominantly non-ferrous, although occasionally ferrous metals can be used too. The primary die casting materials are aluminum, magnesium, and zinc alloys, each with unique properties and applications. Aluminum alloys. Aluminum die casting alloys are lightweight and offer good dimensional stability, making them an excellent choice for complex, fine-featured parts. They also provide good corrosion resistance, temperature resistance, and thermal and electrical conductivity. Common used aluminum include aluminum 383, excellent castability, good corrosion resistance, and moderate strength. Used for housings, covers, and components in the automotive and marine industries. Aluminum 360, high silicon content provides good castability, wear resistance, and low shrinkage. Used for parts requiring high dimensional stability and complexity. Common in automotive and engineering applications. Aluminum 390, excellent castability and corrosion resistance with good wear properties. Used for complex shapes and thin-walled castings. Common in electronics, marine hardware, and hydraulic components. The selection depends on balancing factors like castability, corrosion resistance, strength, thermal properties, cost, and machinability. Improved mechanical properties are usually achieved by adding alloying elements like silicon, magnesium, and copper. When determining if die casting is the proper manufacturing process, you should take some critical considerations, including part geometry. Die casting works best for high-volume production of complex, thin-walled metal parts with good surface finish and dimensional accuracy. Tolerances. Die-cast parts typically hold tolerances of plus or minus 0.005 in/in or better for most alloys. Tighter tolerances are possible but cost more. Wall thicknesses. Minimum wall thickness of around 0.02 to 0.04 in is recommended to fill the die correctly for most alloys. The maximum wall is around 0.25 inches. Alloys. Zinc, aluminum, magnesium, and copper alloys are commonly die-cast. High melting point alloys like steel and titanium are not suitable. Mechanical properties. Die-cast parts have moderate strength and hardness properties, but usually require heat treatment if optimal mechanicals are needed. Post-processing. Some machining and finishing operations may be needed after die casting, which adds time and cost. Piece cost. The high tooling costs mean die casting makes sense financially in medium to high volumes, usually over 1,000 parts or more. Part size. The size of the die casting machine limits maximum part sizes, typically around 2 by 2 by 2 feet. More significant parts may require multiple die-cast pieces assembled. Design. Parts must be designed with appropriate draft angles, radii, etc., to facilitate die casting. Avoiding sinks and minimizing porosity also need consideration. Thank you for your time.